Good? Yeah. George Wall. Okay. It's freezing in here. So we'll start like 5 minutes past. Kind of some places do.
Yeah.
I like it. We are not.
It would help me out, but I don't know.
Well, is there a microphone we have? I mean, if there were one,
I've
I'd
just
put one
felt
up.
things in here before. What's a microphone?
The wavelength,
I
the
mean, I'm
natural
not offended by
wavelength.
microphones, but I think we didn't get one scheduled.
Okay.
I mean, I can.
I might be a geek, so.
That's okay.
So you have
Yes.
Can you go on?
One second.
Go down. I'll go look. I mean, hopefully this won't be too disruptive if they come in about your talk, because they're gonna annoy the hell out of you.
anyway.
Yeah, I don't see anything. So if you just ask them if they've got, if it's easy to do and they can do. I want to make sure we do it in a non-disruptive way. So if they're going to have to come in and like bang around, just forget about it.
It's like church, nobody sits up front.
Yeah, unless they can possibly avoid it. It's like the last thing people want to do is sit in front.
The word sales.
Jessica's coming.
Oh, okay. Okay. Well. What's that?
Did they say they were?
Well, we don't know. I think we're sending somebody down.
And then you would sequence
Oh, because it used to be, it's both the machine learning group and the information group.
Right. The information management is all the ETL stuff, right?
Yeah.
And machine learning. So I started with machine learning, then they told me information management, and then sequence analysis, that's a sequence that we
Moving on to the world.
well, you get, that's least.
Yeah, I'm sure you do. That's a lot of responsibility.
Yeah.
All right, let's go ahead and get started. We're going to get you a microphone. It's coming right now. I'm Sam Madden. It's my pleasure to introduce our speaker today, Joseph. He's going to talk a little bit about the work that he's been doing at Microsoft, that Microsoft has been doing in analytics or big data or whatever it is we have to call it now. But he heads, I guess his bio says he heads something complicated. It's something that sounds complicated, the information management and machine learning group, but he just calls it the data group. This includes, I guess, information management, machine learning, as well as the SQL Server team. So he's got a lot of responsibility. So it's awesome that he was able to come here and help us talk to us about what's going on inside of Microsoft and analytics. Prior to that, he, I guess, ran the CTO of the product team at Amazon.
Oh, the retail team at Amazon.
So I guess the thing that doesn't make any money at Amazon, but the thing that we all know Amazon for. Anyway, thank you very much for coming. It's really it's a pleasure to have you. I'm really looking forward to talking. So, thanks.
Thank you. A bit of the history that Sam didn't say. I've been always in machine learning. My first job at Amazon was as a VP of fraud prevention. And I was always called a VP of fraud at Amazon. So I never lived that name down, and some of those nicknames you get. So
the fraud VP.
yeah, exactly. So today I really wanted to talk to you about analytics, which has been my passion for a long time. And I feel the cloud is fundamentally changing how analytics is being delivered. And that's some of the story that I want to share with you. Cool. That's great. I can manage two things. About 4 years back, Mark Andreessen said, software is eating the world. So he meant that software is in the fabric of our everyday lives, and that's changing everything. But something very interesting is happening 4 years later. The cloud is eating software. That means all types of software are being delivered as services in the cloud. And the way of software delivery has fundamentally changed. And not only is the cloud eating software, but cloud is eating data. And when the cloud eats software and digests data, you get intelligence. Let me tell you what I mean. First, let's step back. In the 1980s, it was just not a long time ago, vast majority of the world's data was analog. There was about 2 zettabytes of it, that's 2 million petabytes. Books, gramophone records, that dominated the world's data. Pretty soon, data became digitized. You had CDs, you had DVDs, and digital data started exploding. And with the internet, that data grew very, very fast. But something very interesting happened at that time. That is, data suddenly started having an IP address, so to speak. It became connected data. That green part is that connected data. And connected data is a fundamentally different type of data than static digital data, because connected data can be moved, it can be integrated with other sources of data, it can be computed on, it completely changes the value of that piece of data. And today, in 2015, as we stand, the vast majority of the world's data is digital. The analog data has pretty much died down, or falling very fast. And at least half of all of that data is connected data that lives in the cloud, comes from mobile devices, comes from the Internet of Things. Fast forward another 5 years to 2020, it's going to be 50 zettabytes of that data. That's 50 million petabytes of that data. The vast majority of it will all live in the cloud. It'll be coming from mobile devices, it'll be IoT and so on, but it'll all be connected data that can be moved, synthesized, and integrated. And that has profound implications for how value is delivered in software. Okay? And let me explain the kind of transformations that happen. Again, a little bit of history. Remember, 50 years back, it was the age of hardware. And it was all about physics. customer experiences were changed by physics. It was faster cars. It was a moonshot. That was the pinnacle of that time. It was faster cars, automation, washing machines and all of that. It was really using physics in every possible way to change customer experience. Then came the age of software. In the age of software, it was all about digitization. You digitized everything. You digitized email, letters to email. That changed how you communicate. You had productivity software like Office that changed the way things work. People moved spreadsheets from paper into Excel, into software. All of that created new customer experiences. Great. So that was all really the age of software, driven by primarily digitization. But now we are in the age of data. Right, the pinnacle achievement that we shoot for is even human intelligence in many ways, data-driven intelligence, aspirationally human-like intelligence, but even perhaps at much bigger scale. And a huge amount of transformation in our lives is happening from intelligence extracted from data. Okay, intelligence that might give you recommendations on personalization, like on devices, personal assistants, online recommendations. Ads are being all completely targeted to you. The vast majority of us are inundated with the results of targeted ads from machine learning. Search engines are all driven by machine learning-based rankers. And so intelligence is driving the changes in customer experience. And that's actually a profound transformation. And it's having an effect even in industries that you least expect. And so let me take some examples. The first story I want to tell you about this here is called a connected cow. So these are the connected cows that I'm talking about. So look at that pedometer on their feet. I have one of them. This is actually a real pedometer. It lasts for about 5 years, counts the steps a cow takes. Every step a cow takes is from those farms are being sent over the wire to a service in Azure, in the cloud, Microsoft's cloud, and it's being analyzed. Why? Do cows need to take 10,000 steps a day? Okay, but before I tell you the answer, so let me step back. Every company today is a data company, even the ones you least expect. Even farms, even dairy farms. Their output is milk and beef. They have constrained resources, expensive farm labor, pasture, food, and they have to maximize their output under the constraints of these resources. So what are the things that a farmer could control? Turns out there are two really important things that they can control. First one is detect health issues early and prevent loss of animals, preventive maintenance, so to speak, or predictive healthcare. And the second one is to improve cattle production by the accurate detection of estrus. Now, if you remember high school biology, estrus is when animals go into heat. That's the only time when they're ready to mate. That's when the magic is ready to happen, so to speak. And it turns out to be an incredibly important control in dairy farms. And for millennia, that has been the case. Now, this shows the effect of estrus detection rate on the pregnancy rate in dairy farms. Okay? It's an incredibly important control for dairy farmers. So these days, with artificial insemination, you get about 70% conception rate in every cycle, which is actually very good. But estrus detection has been done by farmers for millennia in age-old ways. Close observation, essentially, to see if an animal has gone into heat. And the pregnancy rate is then, effective one, is 39%. Now, but what if you could actually use technology to help? Technology has helped here, but it hasn't helped as much here. If you could improve that conception rate to 95%, look at the incredible improvement in pregnancy rate you will get. That's effective calf production in a particular cycle. It's very material for the farmer. So what could you do? Well, it turns out to be, by the way, literally a needle in a haystack problem. Estrus lasts only 12 to 18 hours every 21 days. Like a lot of natural processes, they're not as regular as one would like it to be. And occurs sometimes at inconvenient times, mostly between 10 p.m. and 8 a.m., when farm hands have things to do like sleep. So what to do? Could technology help? Could you develop what to do in a farm with hundreds of cows? Could you develop a heat map of the farm, so to speak? Well, so that's a question a dairy farmer in Japan asked Fujitsu our partner. And Fujitsu's researchers consulted some veterinarians. They came up with an incredibly ingenious system for detecting the onset of estrus, which was actually 95% accurate. This is that system. So there's a pedometers on the feet of cows. And by the way, these days there are thousands of cows in farms in Japan all wearing pedometers. And the step count is being transmitted to a service in the cloud, and the service analyzes the step count data. And when the animals go into heat, they send alerts to mobile phones of the farmer, so the farmer can then go schedule artificial insemination. And it turns out there's a very simple secret to detecting the onset of heat. And let me explain that with a graph. So the x-axis here is time of night, and y-axis is the number of steps a cow is taking. So this is a normal cow on a normal night, walking around a little bit, sleeping a little, walking around a little bit. Let's see what happens when the animal goes into heat. So here's what happens. The number of steps the animal takes suddenly goes up. The cow essentially becomes restless, starts pacing around furiously when it goes into heat. And that signal, it turns out to be 95% accurate for the detection of estrus, onset of estrus. And the optimum time for artificial insemination turns out to be 16 hours later. That's when you get the maximum consumption rate. That's when AI meets AI, artificial insemination, so to speak. And it turns out there is a lot of other interesting things that the data revealed. They found that if in the first 4 hours of that period you perform artificial insemination, you're likely to get a female calf with 70% probability. In the second, you're likely to get a male calf with 70% probability. So now the farmer had an amazing control at his disposal. He could choose the sex of the animal that was being born, and based upon his needs in the dairy farm, he could probabilistically influence that. An amazing control. And Fujitsu went on to study the data, and they found even more interesting things. They found they could detect about 8 different diseases of animals by analyzing the step count patterns over the day. Because different diseases cause different types of listlessness during the day and different patterns of walking and so on. And you could actually detect differences between diseases. So you had for a silent animal, and you could actually do diagnostics in very intelligent ways now using that. So step back a little bit. This is an amazing change. But what is it at the end of the day driven by? It's driven by about 3 different things. First, the ability to digitize every type of behavior, driven by the arrival of the Internet of Things, which is happening all around us. Sensors of all types being attached to so many different things. Perhaps you could all learn a lot more from your Fitbit than you thought you could. Now, and then that data now being transmitted into a cloud where you can actually build software as a service. You shouldn't expect farmers to manage data centers or even services, connected things, and really administer their own software. But now the cloud as a host for the kind of services of this type, analytic services, which, by the way, are actually extremely simple to do. I mean, anyone here in this audience could wire up with today's services available on the cloud, like Microsoft Cloud. You could wire up one of these things in less than a week, in a few days, if you knew a little bit of familiarity with some of the services, and actually launch a full-fledged service like this and roll it out globally in a matter of days, right? But again, the cloud provides the ability to build services like this in a very agile fashion, globally roll it out, and embed over time intelligent analytics based on the data that is being captured, dramatically changing our experience. So let me go on. Another revolution that is happening is in the world of genomics. At the end of the day, we are all data. We have 2 billion pairs of genomic pairs in our cells. They're letters coding for our DNA. And the digitization of all of that is driving an incredibly profound revolution as well. Similar, but in a more profound way for our health. So, and that's driven by this chart. How many of you have seen this chart about the cost of sequencing? Small number of you. The first human genome was sequenced in about 2000, 2001. It took 10 years, $200+ million of effort. And the cost of and time of sequencing a human genome has fallen much faster than Moore's law. And today, it's really less than $1,000 to sequence an entire human genome. Takes about a week. Portions of it can be sequenced in a few days and for $100. There are services like 23andme.com that will do it. And anybody use 23andme.com here? Okay, a small number of people. It's amazing, by the way, what you see when you actually digitize yourself and get the genomes. And they actually have a full social network based upon genomic similarity to other people who have chosen to share their information. By the way, that's also a fun story. I happen to be from a place in India called Kerala, which is a small West Coast thing, and I'm an Orthodox Syrian Christian. And we all sort of happen to have certain specific names, like Joseph, Sirosh, and so on. And what is pretty amazing to me is when I look at my second and third cousins according to 23andme.com, based on genomic similarity, those people all seem to have names like me, which means that the community doesn't intermarry a lot probably, and doesn't actually commingle a lot. But it's amazing what genomics can tell you. So about 4 months back, I wanted to do this with 23andme.com. I sent a sample of my SPET. 23andme.com sent me back a CSV file. We had R supports a lot of analytic packages for genomics, bioconductor, and so on. We analyzed it with MSR's help to find the kind of disease risks that I have. Turns out you can align a genome with genomes of a lot of people who have shared their genomes in public. There's a 1,000 genomes data set, and disease risks of those people. You can compute your disease risk relative to those people and understand where you may have the highest risks. And it's actually very interesting. It's my health being predicted for the future. And this is what I found. This is actual real data. Turns out, by the way, blue is population risk, red is my own. I have low risk for hypertension, but I have about 3 times the population risk for prostate cancer. And that's my future predicted from my data. And now I can have a service in the cloud like Azure where I can take a CSV file that is my DNA, send it to that, and get results back. And that's another thing that is driving an immense potential revolution. In the future, when we go to hospitals, some of the first things that doctors will do will be to get your genome sequenced and compare it with genomes of patients from a very large database to identify disease risks that you have so you can understand your future and manage your health. Okay, so I gave you 2 examples of analytic apps. Let's think about what it takes to build an end-to-end app like this. Okay, so what are the kind of ingredients that you would need? I'll explain with the help of a product that we launched recently. But before I go into that, let me talk about the flows of data that you typically see. This is a very simplified sequence. Typically, you have data being captured by the Internet of Things and events of all types coming in, and intelligence being extracted from that data, obviously using a variety of techniques. But then you either put it in front of people and people drive action from those insights, or you drive automation through rules, right? And rules and other optimization. That's the high-level pattern. And when you talk about the intelligence you want to extract, turns out to be in about 4 different categories. Like the first type of intelligence you extract is you ask the question, what actually happened? This is what traditional databases have always been designed to do. They report on it. They have dashboards. They have all kinds of things that tell you what happened, and you can intelligently query it, and that's useful. Problem with that is usually it requires people and insights to be derived from that, right? People get in committees, in rooms, discuss what just happened, and so what to do about it. There's a lot of delay there. If you're smarter about it, you would actually use principles of statistics to model what has happened and understand why something happened. So you can actually have sound basis for understanding it. So then your time to decision is a lot shorter. You can take better actions. If you're even smarter, you will ask the question, what will happen? And you will have statistical predictions. You will estimate with a certain level of confidence. And that allows you to take decisions that are more robust, faster, and drive action. And if you then proceed a little farther, if you're even smarter, you will then say, knowing what happened, why something happened, and what will happen with the probability distribution around outcomes, what is the optimal thing I can do, right? What is the recipe to follow to get an optimum result that I want, right? That involves a higher order of solving for the objective function you're trying to solve. That then drives to automation, full-fledged automation. That in many ways is our goal, right? At the end of the day, the highest goal of intelligence. Okay, so now this is been our vision really at Microsoft in building out the platform on the cloud. And we recently announced a product called the Cortana Analytics Suite. Think about this as the Office suite, but for analytics. But it is a collection of different components that you would use in constructing those flows and solving these at big data scales. Okay? Now I'll just show some of the key components of it. It's an extensive collection, so obviously it'll take a long time to go through all of it. But there are 4 big pieces. Information management, meaning bring data in and manage it. And it turns out to be a much more complex problem than you think in real world situations. Big data stores, where you store and organize that information in queryable, analyzable ways. And you have to have storage that is married to the kind of work you want to do very often. Machine learning and analytics, okay, there are analytics that can be batch, they can be real time, they can be predictive, prescriptive, all of those. Dashboards and visualizations that are about visually showing it in very nice ways. Cortana is a personal assistant, right? What is interesting about Cortana, the personal assistant, it's like Siri or others, is it is an intelligent assistant that really tailors its output to what you need. It's context aware. It can also give you proactive notifications. It's different from going to a dashboard and trying to browse around. And in a real enterprise, you'll have lots of dashboards. Which dashboard do you go look at? You just go thumb through a lot of pages. When you have an intelligent personal assistant that knows your information need and intent at any given point in time, it can actually be the front end to interact with all of this complexity of the dashboard. It can give you really relevant information. So it uses intelligence to create relevance, right? And based on your usage patterns. And then you have a number of other things. These days, the vast amount of data that is newly created is image data, video data, speech data, unstructured data in general. And from Microsoft Research, there are a number of algorithms for face analysis, vision, and so on. Has anybody here gone to the website how-old.net, howold.net at all? Yeah, it is a site that takes pictures, uses one of these face APIs, recognizes how old you are based upon analysis of the face, and shows you the number. It's actually a fun demo that I launched about 6 months back. So those are there. But again, as APIs hosted in the cloud. Okay? These are like Google Maps APIs or Bing Maps APIs. It just runs in the cloud. You don't have to worry about anything. And you just interface with it. And then APIs for recommendations, customer churn, forecasting, etc. So that's sort of the end-to-end flow. And I want to now focus on a couple of things that are actually interesting to look into. For example, Azure Data Lake. Azure Data Lake is a service in the cloud for big data. Okay? Just an API. You don't need to stand up Hadoop. You don't need to stand up any of those. It's a simple multi-tenant service. It has a store and an analytics layer. The store layer just has a web HDFS API. So it's like a web HDFS API in the cloud. You can send it with big data. You can read from it with enormous I/O. Right? Any application that talks web HDFS can actually use the Azure Data Lake store. So that's a storage layer distinct from the compute layer. Remember, separating compute and storage in data analytics is actually a profoundly transforming. In all of the things that you know about databases, even Hadoop systems, they're all built where these layers are too tightly coupled, especially in traditional databases. And the indexing layer and everything is like mashed all the way up. It's monolithic. When you actually separate the two, you can independently scale the two, and that's actually very, very important, very, very interesting. Azure Data Lake does that. So you have a compute layer that can completely elastically scale. You can have a storage layer that can completely elastically scale. So you can have exabyte size file systems, enormous amount of compute in parallel. Azure SQL Data Warehouse follows the same principle. Separates compute and storage. It's a traditional SQL data warehouse, but the storage layer is separated from the compute layer. Traditional data warehouses like a Teradata or Oracle RAC or Exadata, it's a big iron that sits in a room and just heats it up most of the time, and it's utilized fully only during small portions of the day. I used to run Amazon's data warehouse for 3 years, and by the way, I have scars on my back to prove it, which is why I wear a coat all the time. But it is incredibly hard to do because the data changes so much. Schemas have to change and adapt. It is growing extremely fast. The query volumes are exploding 200% every year. Scaling that with traditional big iron is incredibly hard. Procuring it, managing it, moving it, all of that. With elastic data warehouses, that game is completely different. So whenever you need it during the crunch times, usually midnight to 5 a.m. when you process all of the day's data, you can scale out as much capacity as you want, do all the processing, and when done, you collapse it, and you don't have to have many nodes there at all. And that changes the cost factor dramatically in data warehousing. So that's what Azure SQL Data Warehouse achieves. Okay, so I'll talk about Azure Machine Learning soon, and I'll show you a few other interesting things as well. But one more thing, stream analytics. Stream analytics is also, stream processing is another incredibly important area in big data. Traditional things, even open source things like Storm, requires a tremendous amount of coding in Java and setting up the whole network and so on. It's pretty complex. What we have here with Stream Analytics is a fully managed service in the cloud. It just lives in the cloud. You can go to it, write a SQL-like query to process a time window of data. So flows of data can be set up, and you can have standing queries in those flows of data. You just configure it on a web page, and it does that computation, and the result of the computation can be sent to a dashboard, other big data stores, or whatever. So it makes it extremely simple. So the theme here, by the way, you're probably starting to sense a common theme, and that's this particular theme. Fully managed cloud services, end to end, okay? The thing that is transforming analytics and making it, in my opinion, agile, simple, and beautiful, okay, is when you have completely, fully managed services in the cloud that don't need setup, compilation, hardware, elastic managing, load balancing, all kinds of stuff. Not all of that overhead is completely taken away. And you can just fire it up, you can sign into it, set the analytic you wanted, and go instantly, okay? That changes the way analytics is done. It eliminates an incredible amount of heavy lifting. And then the collection of things I showed you, the complexity of all of that is what has actually prevented analytics and machine learning from blossoming to date. Because if you think about all of this complexity that you saw, if you were to actually buy independent pieces of software from vendors or try to integrate it from open source, it is a nightmare. It's a nightmare to manage, it's a nightmare to configure, it's a nightmare to administer. And when you can simplify that with fully managed services that live in the cloud and have sufficient independence, and you just configure them up together, wire them up together like Lego blocks, you actually have a tremendous elimination of heavy lifting. And that changes productivity in analytics in a big way, okay? And it provides you the kind of abstraction you need to do serious enterprise scale analytics on big data and deploy it in applications. The other important thing about this whole thing, a lot of people in machine learning stop after building the machine learning model. They rarely pay enough attention to how to deploy it in an application, how to integrate it into the workflows, how to manage it, how to update the models, how to do all of those things. You need to think of all of those. These systems actually provide that capability, again, changing the level of productivity. It's also a very simple way to purchase a cloud subscription. Our goal has been to productize, to simplify, and democratize. We're not trying to create a big professional services organization to set all of this up for you, unlike some other companies. And we create a partner ecosystem that creates solutions on this, okay? And that's actually really important as well. You want people to be creating solutions as opposed to wrangling tech and connecting up a lot of open source. And that's our goal. So again, this is our aspiration, to have an analytics platform that creates agile, simple, beautiful analytics. Okay. So now, I wanted to refer to a couple of learning resources, and then I'll give you a few more examples. We just recently had a course, an edX course, a MOOC, run by Professor Cynthia Rudin of MIT, and Stephen Elston, which took some of these services and taught in the cloud. Again, this leads to a new way of teaching, by the way, because these are fully managed services in the cloud. People can just sign up and start doing homework in the cloud on Azure Machine Learning or other things. Changes the way you teach. That class had 35,000 registrations from 170 countries in the short time since it was announced. Okay, incredible. It's funny, even from countries like India, people are learning things. People who have no knowledge of machine learning are signing up, are able to access it, and starting to learn it. It's almost become like, in my childhood, people used to go learn typewriting because it helped them in their career. Now they're learning machine learning because it helps them in their career. By the way, the rerun of that course is on November 13, and you can go get it there. And you get these kind of wonderful certificates, and our CEO's signature is up there. and by the way, across the world, these kind of certifications are actually very interesting to people because it helps them in their professional career, right? Okay. Now, I wanted to now play a video that shows another use case, a case study of how some of these things are being used, this time in healthcare with Dartmouth-Hitchcock Hospital. Do we have audio, by the way?
Yeah, it was.
We do.
The U.S. healthcare system is challenged by the task to deliver exceptional, personalized care at a lower cost. Despite spending nearly 1/5 of our gross domestic product on healthcare, we struggle to meet this goal. Financial pressures on care providers are increasing. This isn't sustainable. So how can we deliver high-quality, personalized care that patients deserve, given the cost pressures we face? At Dartmouth-Hitchcock, we've created Imagine Care, a new cloud-based solution built on Cortana Analytics Suite and Microsoft Dynamics that enables providers to help patients achieve better health. With the help of Microsoft, Dartmouth-Hitchcock is building a technology platform to serve healthcare organizations and patients across the country, setting a new standard for personalized care. Now, using machine intelligence, providers can develop a care plan that's unique to each patient. We can monitor patients from their homes, where data is collected from devices and sent to the cloud, to Imagine Care's 24/7 contact center, where registered nurses continually monitor a patient's health status and potentially serious trends.
Cortana, summarize health status for Ben Andrews.
Ben Andrews' weight has increased more than 2 pounds in the last 24 hours. Please review the home diuresis protocol prescribed by Dr. Phillips.
Patients get reminders and encouragement and dynamic updates to their care plans, improving their health, helping them avoid unnecessary trips to the emergency room, and reducing the cost of care. With support from loved ones and real-time interventions, there is less likelihood of readmission. With Cortana Analytics Suite and Microsoft Dynamics, we're transforming the way healthcare is delivered today, improving patient outcomes, reducing costs, and offering an unprecedented level of personalized care.
Connected patients is the future of healthcare, by the way. About 70% of all emergency room costs are actually avoidable because a lot of it is driven by, especially in developed countries, is driven by chronic illnesses and patients with chronic issues going into emergency rooms. And a lot of these issues can actually, with the right instrumentation, be predicted ahead of time and avoided. Now, my dad, for example, had congestive heart failure. Turns out symptoms of it, with the right data, you can predict this. If you know he had a history of kidney disease, he had a history of blood pressure, he had diabetes, and if he starts to gain weight, and if your weighing machine was connected over the internet to an analysis system, and if you see blood pressure increasing, say from a band or something, you can correlate all of these data points and come up with a prediction on the probability of a congestive heart failure. And that then, when you can identify, it often turns out to be very predictable, very treatable. You can take diuretics to actually reduce your blood pressure. Then instead of coming to an emergency room with a heart attack, you can go visit a doctor who can then prescribe preventive medication to you. A lot of things are of that nature. So it's not just Dartmouth Hitchcock, but University of Washington Tacoma has a whole research program looking into, in this case I'm showing congestive heart failure, but a lot of different chronic diseases, and instrumenting patients with Internet of Things based devices, collecting data, and predicting future health outcomes. So in their estimate, this is actually a flow of looking at it from pre-admission to post-admission to pre-discharge and discharge. They collect data everywhere and estimate probabilities of readmission into emergency rooms. 2013 readmission statistics, by the way, are amazing. Real statistics. There are 7.1 million readmits of patients who should not have been, by and large, readmitted, right? 5.3 million of that is avoidable. And assuming it's about $13,000 each in readmissions, it's about a $13 billion opportunity cost. And these are incredible statistics when you look at it. So the future of healthcare is data-driven and predictive. This is a diagram that illustrates the flow of data. Again, I won't go through all of this. Here is all of the Cortana Analytics suite that I talked about, but they're taking data, clinical and demographic data, claims data, mobile device data, psychosocial data. They're taking all of that and they have a collection of models, a model bank. There's a machine learning models built on top of Azure Machine Learning. And from that, they have a few tools that are being powered, a discharge tool, a retrospective tool, population health, an outpatient tool, and then, of course, dashboards, apps, insights. They've put up a whole workflow to manage patients. And they are testing it with a collection of hospitals. So big data and analytics can truly change lives. Imagine this combined with genomics, the power of genomics and the power to measure everything, and analytics as services in the cloud can dramatically change how we live. Okay, so stepping back, now analytics, these platforms are being built increasingly in the cloud, and the cloud has huge advantages. But the established analytics platforms are all on premises. So Microsoft, we are building at both places. On premises, it's SQL Server. SQL Server is actually the #1 database, believe it or not, and very few people know that. The #1 database in number of installs, and second in revenue, but now marked as the leader in Gartner's Magic Quadrant, for whatever it's worth. It's become extremely popular, and it has a lot of features that, like in-memory features and advanced analytics using column store. We have recently integrated R into SQL Server. By the way, there's one language you should consider learning in the future. It should be R. R, the language of statistics, has vaulted in popularity from about being number 9th in popularity of programming languages in 2014 to number 6 in 2015. Amazing for something so domain specific. And that's driven by an open source community. Every statistician, a computational statistician, now creates packages of their research in R. And now we have taken R, made it scalable, integrated that with a database. And again, here's an area of opportunity for anyone who is into research. The one thing, by the way, that R, languages like R lack, is an understanding of all of the magic that database researchers have actually implemented in databases, about structuring data, about using indexes, about all kinds of things that we have learned about managing data and processing data in databases is very rarely reflected in R. But computational statistics is all about data crunching. So if you can bring the world of SQL and the world of R together, there's a lot of magic to be realized in the future. What we have done as a first step is bring R very close to the data inside the database so that you can easily operate with query processing, SQL-like query processing on the data where that makes sense, and extract aggregates, variables, etc., compute it all in the database, and then use R for the statistical part, or logistic regression or machine learning or whatever. And bringing those two things together makes it much faster. By the way, not only, and that's what I wanted to show in this next diagram. So this is sort of the SQL Server stack. By the way, SQL Server is not just an OLTP engine. It's an OLTP engine, but there is a data warehousing engine. So I have in-memory data aggregation capabilities of all types. There's mobile BI built into it, so cubes, all our cubes and all are built into it. And then now we have R, advanced analytics, built into it as well. And there's one unique thing that happens when you bring R into the database. And that's also very important to understand. Remember, if you do machine learning today in applications, people are actually doing the analytics in the app layer, moving all of the data out from these systems in general, bringing it on the app layer, doing these complex machine learning computations, and then using the results. Incredibly wasteful. You are much better off following the database model. In the database model, you had SQL queries next to the data. You actually put the data management at a different tier from the app tier. And that's exactly what should happen with machine learning and analytics too. So when you take things like R, put it next to the database, make it easy to integrate SQL and R in the same statement. Now you can have the analytics and machine learning run inside of the database with that abstraction between the database tier and the app tier. And that allows incredible flexibility. So apps can become intelligent if they are already using a database, and the intelligence is computed inside the database. And so that's the power of in-database analytics. Okay, so question. How many of you wear a tailored shirt? A small number of people. Look, 40 years back, when I was a kid, everybody wore a tailored shirt because you got textiles, went to a tailor, got yourself measured, got clothes fitted. What changed in 40 years? What?
Mass manufacturing.
Right, mass manufacturing of clothing became so incredibly cheap that clothes of all sizes, shapes, and styles, even designer clothing, could be mass manufactured at low cost, distributed in department stores worldwide, and you could find among the vast selection available what you really wanted. Okay, data science and machine learning today is like tailoring 40, 50 years ago. You go custom get your data, you hire your data scientist, you custom build your model, and you get that tailored machine learning model that works just for you. And it's an incredibly slow process, deploying and managing. The future of analytics is like clothing, when you have mass manufacturing of all types of intelligent applications, okay? It's actually not unlike what you see in an iPhone app store. You'll see 10,000 different clocks in an iPhone app store, okay? But it's possible because developers can actually mass manufacture, so to speak, those applications, surface them in a marketplace where customers can then pick the kind of thing that they like, evaluate how they are, okay? In the case of intelligent apps, it would be by pumping data and seeing if it performs to the way that it is being advertised to perform, and then integrate that into applications. That in many ways is the future of machine learning and data science. And we're starting to take a small step towards that. So this is the Cortana Analytics Gallery, which is meant to be, in this case, it's sort of like a Pinterest of machine learning, if you will. A place where people can publish experiments, APIs, machine learning apps, and people can organically do that. It becomes a marketplace. And it's very easy for someone to go click into that, actually run a machine learning experiment, or take an API from it, like the Face API, and build an application with it. Okay? So let me then, what it has is intelligent SaaS APIs and apps. So let me show you a glimpse of that. So this is that particular website. You'll see experiments, machine learning APIs, tutorials, collections. So if I click on machine learning APIs, you'll see popular machine learning APIs. Face APIs, text analytics, speech APIs. So if I go and click on Face APIs, I'll see a web page with the description of all of that. I'll say sign up for it and try it now. And so it's actually very easy to go try that. I can actually go search for something like anomaly detection. And I'll find an API for anomaly detection. And I'll say, if I say try it now, there is a sample app that's right there on the cloud, and it'll come up, and I'll be able to test it. It's taking a little bit of time to load that particular page. So while I go on there, let me show you other features. So I have collections. Collections are a collection of homework experiments, for example. So there's a book called Predictive Analytics with Microsoft Azure Machine Learning. So this one has all of the example code in there, right? And I can click on any of them and start using them. So the edX course that I just mentioned, all of its experiments are live online. So there is bike rentals, it's an experiment. I can click on it and I'll see open it in Studio. And when I say click open it in Studio, it's going to go open it up in the Machine Learning Studio. Give it a minute. It's actually, this is the actual workflow for that machine learning experiment. It's actually opening it live inside of Azure Machine Learning Studio and showing you the workflow. So what you're seeing here is the workflow of that particular experiment. It's bike rental data, project columns, is selecting some columns, executing some R script on it, executing some Python script on it, applying some SQL transformations, doing some basic linear regression on it, score model, evaluate model. It's live there, okay? You just picked it up and you're executing it in the cloud in Azure. And I can click run and it'll actually execute that experiment live. So it's been queued for execution. It's actually that graph as we speak is getting executed. While that's running, let me actually show other examples here. So here is another one that I opened some time ago. This was a tutorial on building a classification model in Azure ML. This one was about predicting whether you will survive the Titanic or not. Okay, so if you're a passenger on Titanic, you were in a certain class, you had you were male or female, you had a bunch of parameters. You can predict whether you would, what's the probability of you surviving. So this is that workflow, and I'm actually in this case comparing two algorithms, one called two-class boosted decision tree and two-class decision forest. I'm training a model, scoring a model, and evaluating that. And all I have to do here is like press run, and that model is going to be executed in the cloud. And you will see that hopefully it will run fairly fast. It's running. So it's actually finished running. It's now evaluating model performance. And I will show you the model performance right there. I can right-click here, visualize, and I will see two ROC curves. These are ROC curves, one for boosted decision tree and the for regression. Now, you can all try it and go into the details, but that fast, you just got machine learning models trained in the cloud, and those workflows are very easy to modify. And now let me show you another really interesting thing. Let's say I created these models, and I wanted to create a web service out of it, okay? A real API that I can call and send it some passenger data and see if it works. And so the thing to do is to say set up web service. Let's see. Yeah, I need to run it just once because I changed something here. I'll say do a predictive web service. And just watch what happens. So what happened, let me just exit that. What happened right there is as follows. So that graph, that portion of the graph that was data transformation at the top was actually preserved. Okay, so as new records come in through a web service input, you can actually do the data transformations that were part of the modeling workflow. The model that was trained is actually preserved here, that particular one that I selected, and it automatically set a web service output here. Okay, so it's the workflow that would be executed when a single record is sent for scoring. That's been sort of automatically designed for you. And now I can say deploy the web service, and Yeah, I need to run the experiment once. I'll run the experiment and then deploy the web service, and what you will get is instantly a new API being created in the cloud that I can then call from any application. It'll be live. And give it a minute and I'll show you that happen live. So what then is, publish web service, deploy web service, and it's actually doing that. What you get, an API has been created, you've been given the API key, there's a request response API and a batch execution API, and I can actually click on, say, the request response API, and it'll give me more details about how to call that API. There's even sample code. So this is the URL that you would call with that API key. There is sample code. I can see code in Python and R. So here is the call in Python. If I replace ABC123 with that API key and execute this piece of code in any thing, you will call that API and you'll be able to send it data. Okay? And so the deployment of a machine learning model became just a few clicks. It changes the productivity dramatically, okay, in building an application. It's actually, by the way, a full application. Remember, the whole data transformation workflows are there. You can put in new data transformations in that workflow. You can put additional R code. You can put Python code. And you can create a full application that's completely hosted in the cloud with an API. And those kind of APIs can now be published to the gallery that I just showed you and shared with other people. Okay? So that is, in many ways, the future of future that we are trying to create, which is the cloud hosting intelligent APIs and apps that can be connected into from any application you create and can be surfaced in a marketplace. And by the way, these are APIs. APIs are even more powerful than apps. Okay? They're far more powerful than apps in an app store because APIs can be composed. You can create lots of different types of APIs, and different people may create them. You can compose them in applications. You can build extremely powerful higher-order apps. That's the future of machine learning. So let me conclude with a recap of that power of the cloud that is being born before our eyes. Remember, if you step back, the cloud turns hardware into software. Okay? You don't buy hardware anymore. You just provision it as software in the cloud. That is a huge game changer for a lot of things. It turns software into services. You don't worry about installation, management, patching of software, scaling of software. You don't worry about any of those. Those software capabilities are just available to you as services in the cloud. So software became services. And it's turning data into intelligence using the power of all of those. And that's magical. So let me stop there and take questions. Go ahead.
So great presentation. Thank you so much.
Thank you.
I really enjoyed. I like your kind of like simple slogan of beautiful.
Agile, simple, beautiful.
Yeah, agile, beautiful.
Yeah.
And so obviously all the science is really interesting and amazing, but it's all about their applicability in the business world. Right?
Yes.
And you gave that example of the healthcare
Yes.
system. How long did it take to deploy from the POC to the production?
Yeah.
I'm just curious in terms of how beautiful and simple it is.
Yeah, no, it's a great question. It depends on a lot of cases. In real world scenarios like healthcare, most of the time you end up spending talking to people to get access to data. The engineering portion of it is actually very little, especially with these services and things like that. Hooking these things up is actually not very, very hard at all. It takes very little time. Some of those APIs that one of our partners built, they could build these things in a week or two. Plumbing the data, getting access to the data, getting the approvals, getting all of those things takes months, sometimes a year. That's the current state of affairs. That's that initial hurdle that you have to overcome. But the point really is once you have overcome that initial hurdle, any subsequent iteration with that data and expanding the scope of it is incredibly agile. So yeah.
The question.
This particular application, the University of Washington Tacoma is the